I'm going to introduce the ratio test with an example. Let's look at the series, the sum of minus 1 to the k times k squared over 2 to the k. So now that we know about the issue of conditional versus absolute convergence, we can really ask this question: is it either divergent, conditionally convergent, or absolutely convergent? Can we figure out which three of those it is? And one strategy that I'll follow here is, if we can get a yes answer to absolutely convergent, if we suspect that that's what's true, then that tells us that it's definitely convergent, and we don't have to worry about what the signs do. So what we're going to do is we're going to look at what would happen if we strip the signs away. If it still converges, then it's absolutely convergent, and that's the best possibility, and we don't have to worry about the signs at all. They just help. So let's look what happens. If we strip the signs away, the minus 1 to the k, let's just do our usual thing of roughly looking at what's left. Well, 2 to the k grows quite a bit quicker than k squared, eventually, when k is at all large, and of course we care about k very, very large. And so this should be dominated by the 1 over 2 to the k, and that would be a geometric series, and that would converge. Now, we couldn't literally use the comparison test super easily here, because this is bigger than 1 over 2 to the k. We could definitely do a comparison test argument, and in fact the ratio test is based on a comparison test, but it sort of streamlines it in a certain way. So let's see what happens if, so at this point we have stripped off the sign, and we have a conjecture that even stripping off the sign, it will be convergent. In other words, it's absolutely convergent. So we're really going to look just at this guy. In other cases, we're going to have a suspicion that maybe the signs are crucial, and then it would be just conditionally convergent. Okay, so if we look at this one, our idea is that it's somewhat similar to the geometric series with ratio 1/2. But of course, if I look at, say, the 10th term, that isn't literally super close to 1 over 10. It's more like 100. Sorry, 1 over 2 to the 10. It's 100 over 2 to the 10. So it's got this fairly substantial factor. But let's see, what happens with the next one? If I compare the two terms, and I think about what's really crucial about the geometric series, what characterizes a geometric series is that the ratio of each term to the next is always exactly the same number. Here, if the numerators were 1, it would be exactly 1/2. And you know what? If I take the ratio of these guys, the denominators are going to give us a ratio of 1/2. That's trying to make it half as big. And the ratio of 11 squared over 10 squared is not that different from 1. It's 1.21. And if I go out to like 100 squared over 2 to the 100, and a 101 squared over 2 to the 101, then again, the denominator is trying to make it have a ratio of 1/2, which is exactly geometric, and that's nice. We know that that's the kind of decay of terms that causes a convergent series. And the ratio of 101 squared over 100, that's actually quite small. It's about 1.02 if you calculate it. And so this is the idea behind the ratio test. A clever way to sort of conveniently compare to a geometric series is to take successive ratios. So here's exactly what we do. What we do is we calculate L for limit. You could use R for ratio, but we're going to use R for something rather different. So let's calculate L as the limit, k goes to infinity, of the absolute value of the next term over the previous one. Okay. And we want this to be small. So it's important to get this straight, but you just want to make sure you're thinking, hey, I want them to be getting smaller. That's a good thing. That makes the test come out the right way. So limit as k goes to infinity of the ratio. And notice I'm taking absolute values here. This is going to be a test that really only detects size issues. It can only detect absolute convergence. If you've got a series that's converging but only because of the signs, the ratio test is never going to accurately detect that. So that's important. That's why this test appears, at least in our book, in the same section as where we introduce absolute convergence. So we calculate this number. Then there's three possibilities. If L is less than 1, including it might be 0, It's not going to be less than 0 because it's the limit of a bunch of positive numbers, or non-negative numbers. If L is less than 1, then our summation that we started with is absolutely convergent. Which is really good news. So in particular, it's certainly convergent. Convergent in a good, strong, robust way. If L is bigger than 1, well, what that tells us is that when we take the ratio of the two terms, eventually it's looking like a geometric sequence, a geometric series, with the ratio being bigger than 1. And those things totally diverge. It turns out, you can prove carefully, it's in the book. Then this is divergent. Now, here's the trouble, though. Like with a lot of calculus type tests, there's some sort of gray area or some sort of borderline case where it doesn't tell us as much information as we'd like. Ooh, I don't really need to go like that. Okay. If L equals 1, then the test gives no information. It's not like it doesn't say it's conditionally convergent, for example. It just says, I don't know. It is kind of borderline, but it could well be divergent or conditionally convergent or absolutely convergent. It really does not give any information. So let's see how that works with this series. We have guessed, based on a more informal comparison to a geometric series, that it's convergent. So here, the limit L, limit as k goes to infinity, of absolute value of ak plus 1 over ak. The absolute values strip off the minus 1s, which was our plan in the beginning. And then you have to do the fractions carefully. And where the ratio test is a smart test to do is where this kind of limit is relatively easy, and especially when you get nice cancellations when you take the quotient of one term to the next. So we're going to get k plus 1 squared over 2 to the k plus 1, and then divided by k squared over 2 to the k, and that flips, so we get times 2 to the k over k squared. And here we get, from the geometric part, if you have some sort of part that's obviously geometric, it's built out of stuff and part of it is geometric, then you should get a cancellation that exactly gives you a constant. So that says if the k squared part weren't there, we would just get ratio 1/2 as a constant. The limit would be trivial, and that would be confirming that a geometric series fits in well with the ratio test. Now, what about the limit of k plus 1 squared over k squared? Oh, we know how to do that. We know it's 1, but if you want to do it carefully, remember you do, like, maybe expand that out, maybe a little bit more obvious. Multiply by 1 over k squared on the top. There's still on the 2 on the bottom. K squared times 1 over k squared on the bottom. That goes away. Then that's going to be a 1. That's a 2 over k. That goes to 0. That's 1 over k squared. That goes to 0. So the whole thing is 1/2. So as we confirmed with a little bit of experimental evidence, eventually the ratio between any successive term and the previous one is 1/2. And notice that this is saying the next one is smaller than the previous one because the ratio of next over previous is smaller than 1. That's important. That's why this has to be in the right, done in the right way and not having the fraction flipped here. So this is less than 1. So our series was absolutely convergent. And that's what we guessed. So notice the minus 1 of the k was a bit of a red herring here, that this would converge without it and with it. It's certainly going to give different numbers. It's going to converge a little faster maybe with the minus 1 of the k, but not a whole lot. But for this kind of test, that's the kind of thing that doesn't really matter because this is a test for absolute convergence. All right, that's long enough for this one, and maybe we'll do another example, another one.